Hello, everyone. My name is Miguel Velez, and today I want to talk about white box analysis over machine learning, modeling the performance of configurable systems. So most of today's software is configurable, which is useful for users who have different needs who can configure a system differently by enabling and disabling options, as well as useful for developers who can build and maintain a single flexible system where they can implement additional features to satisfy additional requirements in terms of functionality and quality attributes. And one quality attribute that users and developers are interested in these systems is performance in terms of execution time, since usually they want to run their systems efficiently. So they typically need to make trade-off decisions between performance and other quality attributes and functionality in the system, such as security, safety, or which login level to use. But these configurable systems are a bit problematic, and that is because of the numerous configuration options that they have, which are often cryptic and not well documented, which makes it difficult to know how these options and their interactions affect the performance of the system, which results in a problem in terms of how can we describe the performance in exponentially large configuration spaces. In these situations, users and developers want a function or performance influence model from configurations to execution time that describes the performance of a system over the entire configuration space in terms of its options and interactions. To generate these models, users and developers use black box approaches which use some sampling strategy to select numerous configurations, which they use to measure the end-to-end execution time of the system, which then they pass that information to a machine learning algorithm to generate the performance model. And depending on the learning algorithm used, the resulting models are represented in different forms, such as sparse linear models, decision trees, random forests, and neural networks. But there are several issues with these machine learning approaches. One of them is that we typically need to sample more configurations to obtain more accurate models, but this increases the cost to generate such models. Another issue is the fact that for the same sample configurations, random forests and neural networks tend to create more accurate models than sparse linear models created with linear regressions, which is fine if you want to use the models to make accurate predictions, but it might be problematic if you want to use the models for understanding and debugging purposes. And that is because of how interpretable these different representations are, which has been discussed in a lot of research, but no consensus has been made on how to measure interpretability. But based on our observations and according to many researchers, sparse linear models are considered as inherently interpretable, since users and developers can directly inspect the models to reason about factors and make and understand predictions. Whereas many researchers argue that deep decision trees, random forests, and neural networks are not inherently interpretable, as humans would have to reason over multiple paths to understand the average effect of options and interactions. Because of these issues, our goal is not to use sampling nor machine learning, but rather to use program analysis to efficiently build accurate performance influence models, specifically sparse linear models that are easy to interpret for users and developers to understand how options affect performance in the implementation. So let me show you how our white box approach efficiently builds these accurate and interpretable models. So our white box approach relies on two insights, which we call them compositionality and compression. Compositionality is the fact that performance influence models can be built by composing models built independently for smaller regions of code. So instead of measuring the performance of the system end-to-end to build a model, as black box approaches do, we can decompose the system into multiple regions, measure the performance of those regions to build local performance models for each region, and subsequently compose the local models to get the global model for the system. So if we decompose a system into multiple regions, and if we know which options affect the execution time of each region, which I will show you later how we obtain that information, then we can measure the execution time of all paths in the region with a more targeted set of configurations to build a local linear model for each region in the system. Subsequently, we can aggregate or compose the local models to build a global linear model for the system. Compositionality helps reduce the cost of building models because a few options tend to interact in smaller regions in the system. So instead of measuring numerous configurations to explore all paths in the system, we can measure fewer configurations to explore all paths in each region. So that is how compositionality works. Now let me talk about compression. Compression is the idea that we can simultaneously explore paths in multiple independent regions with a few configurations. Similarly to compositionality, if we decompose a system into smaller regions and we observe that different options influence the performance of different regions, which I will show you how we do that later, then we can measure in a single execution the influence of different options in different regions of the system, thus reducing the overall number of configurations to build a performance model for the system. Compression helps reduce the cost because few different options tend to interact in different regions. So instead of measuring and building performance models for each region separately, we can simultaneously measure the influence of options on different regions in the system. This problem is similar to the set cover problem in which each region has constraints of partial configurations that we need to explore. And we use a greedy approach to select configurations to cover those constraints. For instance, these two configurations cover the partial configurations to explore in this region. Likewise, these four configurations cover the partial configurations to explore in this region, and so on and so forth. So these are the insights of our white box approach. With compression, we can simultaneously measure the influence of options on different regions in the program. And with compositionality, we build and compose local linear models to obtain the global linear model for the system. But these insights relied on the fact that we know which options influence the performance of the regions in the system, which we find using a taint analysis. Specifically, we use the dynamic taint analysis provided by Phosphor, which we use to track how options are loaded and are propagated through the system to control flow decisions. With this information, we can then determine which options affect the performance of each region in the system. So these are the three components of our white box approach. First, we determine which options affect the performance of different regions of the system, which we do with a taint analysis. Then we measure the performance of the regions in the system, and thanks to compression, we can simultaneously measure the influence of multiple options on different regions in the system. And finally, we build the performance model for the system. First, building local linear models for each region, and then composing the local linear models to get the global linear model for the system. So now let me show you how we evaluated our approach with existing black box approaches that use machine learning. We compare our approach, Comprex, with 40 combinations of sampling and machine learning approaches. We use 4 subject systems, which included 2 databases, an indexing library, and an image processing library. And we evaluated the cost to generate the models and their accuracy and interpretability. I will show you the results for one of the subject systems, density converter, but the results are similar in the other systems that we evaluated. Our results show that Comprex, our approach, is comparable to the most accurate machine learning approach, random forest with 200 randomly selected configurations, but we're much more efficient to generate the performance models. When we consider interpretability, our approach, which builds linear models, is much more accurate than other approaches that also generate sparse linear models, such as a stepwise linear regression. And we are similarly accurate to other approaches that are considered to be hard to interpret. And overall, our results show that our white box approach efficiently builds accurate performance influence models, specifically sparse linear models, which are interpretable and can be used for debugging purposes. To summarize, today I wanted to show you our white box approach that does not use sampling nor machine learning techniques, but instead uses program analysis, which efficiently builds accurate performance influence models that are easy to interpret for users and developers to understand how options affect the performance in the implementation.
Thank you. Hi, everyone. If you're just joining us, welcome to the session on performance modeling of highly configurable software systems. I'm Carolyn Seaman. I'm from the University of Maryland, Baltimore County in Baltimore in the United States, and I'm your session chair. And I have Miguel with me, who was the presenter that you just heard, and he is ready to take your questions. So let's jump right in. We have a question from Jonathan, who says, very cool work. And he asked, did your evaluation reveal any instances where the data flow analysis didn't detect real interactions between configuration variables, maybe due to implicit flows?
Yeah, so right, that's a good question. We did see in Apache Lucene that when we were doing some debugging of the methods that we analyzed, that we were not getting quite accurate results. And we digged a little bit more and did a little bit more debugging and sampling, and we saw that, yes, some of the interactions of options were not being correctly captured by the dynamic taint analysis that we use. So we don't know if it's specifically because of implicit flows, but in Apache Lucene was the one and only instance where we did see that case, that the correct interactions were not being captured.
Cool. So I have a question while other people are writing stuff in the chat, hopefully. I was wondering if you could talk a little bit about the relationship of your work to the work that was described in the previous presentation by Max Weber on white box performance influence models. And I wonder if this isn't my area, but it seems to me these look like they're two different approaches to the same problem, but maybe there's just an overlap and they're not quite addressing the same problem. So I wonder if you could talk about how the two compare, how they complement each other, or how they compete with each other, and whether they've ever been validated directly comparing the two approaches.
Mm-hmm. Yeah, so I think both of our approaches are addressing one of the same goals, which is predicting the performance of large configuration spaces. One of the main differences is that in the previous paper, they measure methods individually, similar to what we do, with the difference that they use sampling at the method level, and they use machine learning to extrapolate from incomplete information, whereas we leverage the dynamic analysis to know what are all the relevant information that we need to measure for individual methods to make an accurate prediction. And no, we haven't done a comparison between those two since, yeah, we were working with on our approaches in parallel. But I think that, yeah, like it would be interesting in the future to see, yeah, how is that, these a completely approach that does not use any machine learning compared to this different and innovative way of building these performance influence models.
Do you think that, again, you would find this out if you did sort of a head-to-head validation, but can you imagine that there are particular contexts, particular types of configurable systems, or different, I don't know, different context variables that one of the approaches might work better than the other? So they might have different strengths and weaknesses.
Mm-hmm. Yeah, I think that like black box approaches excel in that they don't need that much setup. They don't need to be that intrusive in the analysis of the systems when they go through our approach. So they can definitely consider a lot more configuration options, not only binary options, but also numeric options. So I think that that's one of the great benefits of using the black box approaches. I think, yeah, the white box approaches that we have researched for the past few years, the benefit is that we can understand what is happening internally in the source code. So as Max and I have looked at that, we can know which methods are being influenced by which options, and how is that those options are influencing those methods. And I think that that's one important piece of information when developers have to debug any performance problem, which is actually what I'm currently working on as future work, or as moving forward from this paper. That yes, the benefit of a black box approach might scale to larger systems. There's a lot less setup, but if there is a performance problem and now a developer has to go and debug, they are faced with this potentially huge code base, and yeah, they don't know where to start. So I think, yeah, that's one of the benefits of using white box approaches.
Makes sense. All right, thank you. Any more questions from the audience? I'll give you a few more seconds, but if not, we'll end the Q&A a little bit early. But don't go too far away. There will be a discussion room where you can talk with Miguel one-on-one or in a much smaller group to talk about his work further. There'll be a box popping up in about 4 minutes with a link to that discussion room. So if you're interested in joining that discussion, don't go away. Watch for that box to come up. And it looks like there are no more questions, so we'll end the Q&A. Miguel, you can stay here or you can leave the room, but don't forget about the discussion room, and there will be another presentation starting in about 3.5 minutes. Thank you very much.
Thank you so much. Thank you very much.